Okay, guys. So, very good morning to all of you. Today we are going to discuss. Today is the sixth lecture of the advanced manufacturing processes, and we are going to discuss about the electric discharge machining. Okay. So this is part one, in which basically I will brief you in the second slide that what we are going to do. But before starting the EDM process, I just want to brief you that in the last three lectures, basically we discussed about the electrochemical machining operations, and in the last lecture we have almost done two numerical problems. Okay, and one of the numerical problems that I gave you in the homework, so like just to cross check the answer, uh, I'm going to take first this one, then we will move to the theoretical part. Okay, and I will brief you before going to the EDM process that what we are going to discuss and what we will discuss okay in a content portion. So the students are still joining. Actually, I think that this timing has been maybe changed. That's why they are getting late.
So actually the class timing was 9:30.
Yeah,
That's why
yeah, exactly. That's why I'm thinking the same thing. Okay, so let's start with the problem so that let the other people join. Okay, during by the time. So, okay, guys. So please be ready with your calculator for this question. So the composite of a nickel superalloy is as follows. Because like in this problem, we have to use the electrochemical machining operations and whatever the workpiece is there, that is made up of the nickel superalloy. Okay, now there are different types of the superalloys of the nickels is available. So what percentage is here given to you, that we have to consider. Okay, so nickel percentage is 70%. Okay, the second is the chromium, that is 20%, the iron which is 5%, and the rest is titanium. So guys, total nickel superalloy will be 100%. Okay, means individual elements are added and it will become total 100%. So if you will see, then nickel is 70%. Okay, chromium is 20%, so this will become 90. 70 plus 20, 90. This iron is there, so this is 5%, so it will become 95, and rest is the titanium. So how much is remaining? 5%. Okay, so please keep in mind this one. Okay, now calculate the rate of dissolution. Rate of dissolution means the feed rate. Here they are talking about the feed rate. Because dissolution, when dissolution means the depletion of the material starts. The depletion of material starts when the material start removing from the workpiece surface. So what rate will depends. That will be the feed rate. That with respect to what feed rate we are keeping the tool towards the workpiece side. Once it will come in contact with the workpiece, minimum gap will be there, then it will start depleting the material. So the rate of dissolution is nothing but the feed rate only. So this is asking to you. Okay, so this is feed rate. And what will be the feed rate? That is equals to material removal rate upon the surface area. Okay, or S we can say. Fine. So let's see, if the area of the tool is 1500 mm square. So this is S is given to you, that is surface area. Now here the surface area, this area is given to you of the tool. But as I already discussed that if this is the container, okay, and up to this one we have filled the electrolyte, and these are the two, this is the workpiece and this is the tool. So if I'm, and this is connected with the power supply. Okay, so this is the workpiece, okay, which is the anode side, and this is the tool, which is a cathode side. Okay, now here it is talking about the area of the tool. So this will be the area. This will be the area of this side. Okay, this will be the area. So this is area is 1500 mm square. If this is 1500 mm square, then same when it will move in this direction. So whatever the area of this tool is there, same amount of the area from which basically the material will be removed. Now there is a possibility that this area can be greater than what is the area of the tool. So if it is more than that, then initially it will remove the material from this 1500 mm square area, then we will have to move in other direction. Okay, so this area of the workpiece that will initially it will come in contact, that will also be like 1500 mm square only. Okay, fine. So the current of 1000 ampere we are using, so the value of I is given to you, is being passed through the cell. So electrolyte cell, that is a complete circuit we can say. Assume this solution to take place at lowest valency of the element. So these are the data that is given to you, that is atomic weight, atomic weight for all the elements, that is nickel, iron and chromium and the titanium. Similarly valency and the density is given to you. So first of all if we want to calculate this FR, that is feed rate, so first of all we need this material removal rate and the surface area. So here in this problem the surface area is given to you, that is 1500 mm square. This is mm square. Okay, now you have to calculate the material removal rate. So how we will calculate the material removal rate? First I'm just briefing that what the procedure we will follow, then we will put the data, okay, and get the answer. So how we will calculate the material removal rate? For the material removal rate will be equals to I into A by rho VF. Okay, guys. Now here we have to use the rho. Reason is here the surface area that is in meter square, mm square only. Okay. So whatever the feed rate here we are considering, that will be in mm cube per second. Okay, so that only then only this mm square will be cancelled out. Okay, and whatever the feed rate unit that will you will get it from here, that will be in mm per second. Okay, so we want to calculate the material removal rate, so we are using this formula. Okay, now I is given to you, A is given to you, rho V is given to you, F if not given then we will consider 96,500, and rho is given to you. But guys please listen, uh, first of all we saw the problem which is based on a single element which is iron. Then we discussed of the problem which is based on a binary joint or binary alloy we can say, in which that is gate 2008 question. Okay, in which this is that will be equals to I into this is E equivalent upon rho equivalent into F. So in that problem, in the binary alloy problem, the density of that binary alloy was given to you, and the rho E equivalent, which is a electrochemical equivalence, that was not given to you. But for that, two elements, binary means two elements are there. So for both the elements, atomic weight and the valency were given to you. Through that, we calculated the value of E equivalent and we kept there. Okay, and we get the answer. But here the E equivalent you have to calculate, because for all the elements there are total four elements. This is a quaternary, we can say it is a uh, the combination of we can say quarter alloy. Okay, so because four elements are there, so these for four elements the atomic weight and the valency is given to you here, and for the density is, it's not a single density of the quaternary alloy is given to you, but for all these elements the density is given to you. So here you have to calculate the rho equivalent as well as you have to calculate the E equivalent. So let's move one by one. First of all we are calculating the E equivalent. Is it, are you getting my point guys, why we are calculating this one?
Yes, sir.
Okay, great. So now E equivalent, how we can calculate this E equivalent? Either like we can use this 100 by E equivalent, that will be equals to x1 upon E1, x2 upon E2. Now I am just considering this is a first alloy which is a nickel. First that is nickel, second that is chromium, third which is Fe, and the fourth one this is titanium. Okay guys, so now x1 by E1 plus x2 by E2 plus x3 by E3 plus x4 by E4. Okay, so from here E1 is A1 by V1, E2 is A2 by V2. So if you will keep this A1 by V1, so this will become x1 into V1 upon A1. Okay, So this will be equals to, now why I am taking this 100, because as I already mentioned you in the when we were deriving this formula, that if I am taking this whatever the data that is given to you, like for an example this is nickel is 70% is given to you, then I will put it here 70. If I am taking this 100 over this side, if I am taking 1, then it will become 0.70. So it's automatically like just you are dividing this 100 over this side. Okay, so I'm just taking 1 only. Okay guys, so there will be a less calculation. So 1 by E equivalent, that will be equals to x1 for the nickel, that is 0.70 into V1. V1 is how much? Please check. This is the valency of, okay guys, let's take one more step. This is x1 into V1 upon A1, okay, plus x2 into V2 upon A2, plus x3 into V3 upon A3, plus x4 into V4 upon A4. Okay, so all the data is given to you, just put the data and get the answer. Okay, so this is x1 will be equals to, that is 70%, so this is I'm taking 0.70 into V1 valency for the nickel, this is 2 upon atomic weight for the nickel, that is how much it is, 58.71. Okay, so this is 58.71. Okay, next is x2, for x2 for the chromium, so this is 0.20 into valency, this is 2. Okay, and the atomic weight, that is 51.99, plus x3 is for the iron, so for iron the percentage is 5%, so this will become 0.05. Okay, into valency is 2 upon atomic weight is 55.85. Okay, next is x4, so x4 will be for the titanium, how much percent is remaining, this is 5%, so this is 0.05 into valency, that is for this titanium is 3 and the atomic weight is 47.9. Okay, so guys please tell me the value of E equivalent from here, calculate it and tell me. I'm waiting. At least I need 2 3 answers so that uh, you can justify. Okay, so Aman, I'm expecting the answer from you. Ibad, if you
Okay,
are
sir.
here, then I'm expecting the answer from you. Danish, if you are here. Okay. Umar,
12.63.
I'm expecting the answer from you as well. Umar Aziz, 1856. Okay, so, okay, who is, anybody saying answer?
Sir, 12.63.
Muneeb, you are also here. Sorry, I forgot. 12.63.
63.
What is the unit? No, no need for unit. There is no unit because that's a weighting, atomic weight in the valency. Please, guys, cross check this answer. Anybody else? Apart from these, whatever the name that I mentioned, if you have calculated, you can also mention. Majid, are you here?
जी sir.
Okay, so please tell me the answer of E equivalent. How are you now today?
Sir, fine.
Great.
So 1 minute. एक second.
Please, guys, tell me the answer. Munib, this answer was of E equivalent that you are getting.
So 1.6.
Uh, the answer of E equivalent, Aman.
Yes, sir.
Okay, this is 1.6. Guys, please cross check. At least I need 2 answers, at least 2 to 3 answers that will match with each other, so that we can say, okay, this is the correct. Because there is a possibility to mistake in the calculation while calculating? First of all, guys, you just calculate the value of this one, that is here in this right hand side, okay, and this value will be equals to 1 by E equivalent. So just reciprocate it, whatever the value that you are getting in the right hand side after calculating this, just reciprocate it. Reason is this value is not of E equivalent, that is the value of 1 by E equivalent. Actually, I'm waiting, guys, because I'm getting some different answer. That's why I'm just waiting for the answer which I'm getting.
That's 27.42.
Yeah, that's now Ibad and mine is same.
27.42.
27.42. Guys, please check this answer. Munib and Aman, please check this answer if you can,
Okay, sir.
because I'm
Yes,
also
sir.
getting like
42.
Asif. Okay, okay. I'm also getting like 27.42 only. That's why I'm just waiting for you guys. Okay, guys, if you are doing it, then it's good. Otherwise, shall we proceed for the next one? Okay, so let's move to the next one. We are considering that this answer of this E equivalent will be equals to 27.42. Okay.
जी sir, 27.42 आ रहा है sir.
Okay, great, great, Aman, great. So now, guys, let's move to the next one. That is, we have to calculate the value of 100. This one, E equivalent. Okay. So E equivalent is calculated, rho equivalent. So for the rho equivalent, I am keeping this. We have the same value, same kind of formula, that is 100 by E equivalent. Sorry, rho equivalent, and that will be equals to x1 by rho 1 plus x2 by rho 2 plus x3 by rho 3 plus x4 by rho 4. Okay, guys, so again same the thing. This is if I'm taking considering it 70, then we can take it 100, or if I'm considering over this side as 1, then I have to replace it with 0.70. Okay, now let's see the what is the density value is given to you, that is 8.9. But guys, here the I forgot to mention the unit of that. Okay, so please consider it in gram per cc. Gram per cc, whatever the density values of all four that is given to you, that is in gram per cc. Okay, so now here that will be like, first we are considering it for the nickel, so this will be like 1 by rho equivalent, that will be equals to x1, that is 0.70 upon rho 1, the density of nickel first. So this is 8.9, so I'm just keeping this as 8.9 plus x2 is what, that is chromium and the 20%, and the density is 7.19, so this is 0.20 and the density will be 7.19. Okay, next is the iron, and the percentage is 5% and the density is 7.86. So this is 0.05 upon 7.86. Okay, plus rest is the titanium. So this is 0.05 upon how much the density is, 4.51. Okay, so this will be equals to 4.51. So guys, please check the value and calculate this one and tell me the value of rho equivalent, because here whatever the value you will
8.06.
get it, that will be equals to,
8.07.
okay,
8.07.
8.07. Okay, can I ask you the unit of this, Ibad? Because all the densities that is
Gram
in
per cc.
gram per cc, right? Very good, this is in gram per cc. So this is the, please cross check the value, guys. Guys, can you please tell me the value?
So 8.1 I am.
8.1. 1 is like, come on, because like point, this is value is greater than 5, so that's why 8.1 you
Yes,
can
sir.
consider.
Yes. Yes.
And I think you are keeping your calculator up to one digit only, that's why you are getting
Yes, sir.
8.1. Okay, okay.
Yes. Sir.
So I now two values, both everybody is getting this value only. So I'm considering things 8.07. Okay. Now what we have to calculate exactly, first of all, that is MRR. So that will be equals to I into E equivalent. By the way, we have to calculate the feed rate, but we for that we have already know the surface area. We just have to calculate the MRR, so that we are calculating. Okay, and this will be like rho equivalent into F. Okay, so this just put the value, that is I is how much, that is the 1000 ampere. Okay, so this is 1000 into E equivalent. E equivalent is how much we are getting, so this is 27.42. So this is 27.42 upon rho equivalent, this is 8.07 into F, that is 96,500. Guys, here I'm if I'm considering that this is in gram per cc, because that I already mentioned in the formula beginning itself that this should be in gram. Okay, whether it is in cube or meter cube or cc, that depends, but it should be in gram. Okay, so now it is in gram, so there is no need to convert this one, because in 10 to the power minus 3 or 10 to the power 3. Okay guys, so now whatever the value that you will get, the unit of that will be in, because here it is cc, so cc per second, that will be the unit that you will get at the end. So can you tell me guys, what is the value that we are getting of MRR from here?
It's 0.035.
Yeah, good. This is 0.0353 that I'm getting. Okay, and the unit will be gram cc per second. Anyone please confirm this one?
Yes, sir, it is right.
Okay, great. So this is the material removal rate that we are getting, but this is not the final answer. We have to calculate the feed rate. So feed rate will be equals to MRR upon surface area. Okay, so MRR upon S. MRR will be, that is 0.0353. Okay, this is cc means semi cubic centimeter per second, and this will be like upon the surface area. So surface area is given to you, that is 1500 mm square. So let's keep it 1500 mm square. Now either you can convert this square into centimeter square, or you can convert this semi cube into the cube. So like 1 centimeter equals to 10 so what will be easy if you will convert this one? So if you will convert this one, you just have to like 1 centimeter equals to 10 so cube, when you will do the cube, this will become 1000. Okay, so just I'm multiplying with that 1000. So 0.053 into 10 raised to power 3, this will become cube per second. Okay guys, and this will be like 1500 square. So this will be cancel out, and this will become per second. So can you tell me guys the value of this FR from here?
0.0235.
0.0253.
0.0233.
233.
0.0235 आ रहा है.
Okay, okay. 0.0233 we can, or 34 we can consider. So that will be in per second. Okay, guys. So now here, by the way, it's not mentioned that in which unit you have to consider. So we are just considering this one only. And if they ask that calculate the value that in per minute or cc per minute or cc per second, so that now we can convert. Okay, so this is the final answer. Okay. So I hope that you understand the whole process, or as well as the numerical problems. Okay guys, so if you have any doubt, again I am giving you 1 minute, you can ask me throughout the ECM or in the problems. Otherwise, we should move to the next one.
previous
Ibad,
slide. Previous slide. दिखाइए sir.
previous slide. This one?
Yes sir.
Okay, tell me.
सर स्क्रीनशॉट लेना था अब दूसरी वाली दिखाइए प्लीज
No, Ibad, actually no need for this one. By the way, if you are taking, that's good. But I will share this annotated PDF with you guys. Okay,
okay sir.
fine.
Yes sir.
Okay. Okay, guys. So let's move to the our main topic today, which is the which is the electric discharge machining. And I'm just briefing that what will be the things that we are going to consider, or that we are going to study in like most probably in 2 3 days or 2 3 lectures. Okay, so first, this is the content of the EDM process. EDM is nothing but the electric discharge machining. Okay, electric discharge machining. Now last process that we studied, that was ECM, so electrochemical machining operation. So there we were using the chemical, here we are using the discharge to remove the material. Electric discharge we are using. Okay, now how this electric discharge will be formed, that we will study. For that also chemistry is required. Okay, so we can say that here, along with the electrical energy, we are also using the chemical energy is also dominance. By the way, main deformation is not due to the chemical, due to the electric discharge only. So that's why we are calling it as the EDM process. Okay, so these are the things that we are going to study. So first of all, I will brief you about the literature, that how this process came into existence. Okay, then we'll discuss about the principle and the working part. Okay, then we will discuss about the material removal rate, that how the material can be removed, or the material is removal takes place in this EDM process. Okay, because as I already mentioned that all these are non-conventional machining operations, non-conventional or unconventional machining operations we can say, where the tool and the workpiece is not in contact. Okay, without contact the material is removed. So how the material removal is takes place, this is very important in all the processes. Okay, and especially the four processes, which is like ECM, EDM, ultrasonic machining, and the abrasive jet machining. These four are very important processes. Okay. Next, we will discuss about the dielectric fluid, that what are the properties or the functions that is required for the dielectric fluids. Similarly, for the electrode material, because both the things we discuss in the ECM as well, that whatever the chemical that we are using or the tool material that we are using, what are the characteristic or what are the functionality should be required while selecting the material. Then we will here we will discuss the material removal rate, but here we will make this material removal rate formula. Okay, because here it is not it's a electric discharge machining, so a complete electrical circuit we are using. Guys, it's very important to teach you guys, because this process, because these processes are not completely mechanical, so that like ठीक है, lathe machine में study कर लिया, milling machine में study कर लिया, this cannot be possible. Okay, this is like here all these processes are a combination of mechanical, electrical, chemical energies. So it's habit that mechanical engineers are always be focused towards the mechanical or conventional processes only. They won't consider on the non-conventional part. So that's why there is a need to study these things. Okay, so then we will discuss about the modeling. We will discuss how the material removal rate can be found for during the EDM process. Then we will discuss about the types of the generators. So there are four types of the generators that I will just brief you, and one among them, which is very important, and the complete process is based on the RC circuit. So that we will discuss. Okay, and then at the end we will discuss about the numerical problems. Okay, guys. So today I will try to cover up to the working part. Okay, then tomorrow in the next lecture we will discuss from the material removal rate. Okay, guys. So let's start. So okay, guys, so I'm just briefing. These all the points has been written to you for written to that you can easily understand what the things is. By the way, all these maximum I am covering from the PN Rao book. Okay, because that's a standard book, and I also found that that's good data is good content is given in that. Okay, so first of all, guys, there was a chemist, or by profession he was an automotive engineer, that is Joseph Presley. in 1966, when as I said that he was an automotive engineer, but by profession he was a chemist. So he was working on he has own garage. Okay, and he was like just think when he was looking looking once working on a cars, okay, and especially on the car batteries. So he found that after every time there is a erosion. Now erosion is what? The removal of the material, removal of the material on batteries. So like I am aware that all of you are maximum of you have the cars at home, and when you will open that car, okay, and you will see the battery portion. Okay, so on the battery where these two electrodes are mounted, anode and the cathode, you will see that the material, after some time the material is deposited, okay, and some amount of oil is spill over that surface. Okay, if you have not seen yet, see today or tomorrow or in future, you will found that there is a material is removed. Now this material in the it will be like a depleted material which is removed from these anode or the cathode parts where the electric discharge actually occurs. Okay, so he basically mentioned that he first discovered the electric discharge on the cathode surface, which was left due to the erosion of the craters, because whatever the material that is removed, that is due to the erosion. Okay, and since then arc came into existence for the necessarily or not necessarily for the removal of the material purpose. Okay, but that time this invention was based on the arc. He was thinking like there is a arc is generating, because what is actually happening, because whenever you are starting an engine, just I'm talking about a petrol car for an example, here we are using the spark. Okay, so is how this spark is generated by using the uh, like uh, by using the electric car on by, sorry, electric battery only. Through this only this electric supplies is come whenever we are switching on or we are turning on this car. That time basically what is happening, the complete discharge means power is initiated from the electric battery only. So at the cathode basically the material is removed. So what is the reason of that? That is not given by him, but he just invented that first that there is an electric discharge due to the erosion of the craters. Okay, now let's come to the 1943, which is like just after 180 year after the 180 years. So there was two researchers, okay, or scientists we can say, that is Boris and the Lazarenko at the Moscow University. They got an assignment, okay, which is of which is related with the aircraft that was damaged after the during the Second World War. Okay, and when they were working, their investigation were based on the wear that is caused due to the sparking between the tungsten electrodes. Okay, okay, so they were working on that, and by different kind of studies, they during their experiment they found that, or they noted that the spark were more uniform and the predictable in oil than in air. Means whatever for an example, in the kitchen, to give a flame to the stove, we are using the spark means the lighter that we are using, that is generating the spark. Here guys, please concentrate. Here the arc is not important, but the spark is important. Now what is the difference? Arc means the simple lighters. Okay, simple lighters, on all of you are aware about the lighters. So lighters we are using, that is generating basically the arc. Okay, but I'm talking about the lighters we are using in the kitchen, that is not generating the arc, but that is generating the spark. Please keep in mind guys, here we are talking about the kitchen stuff. Okay, so so the spark which is generated, that is more uniform, means the uniformity is more, that spark in the oil is comparatively uh, in the air. Now how it is more predictable and more uniform is like, if you will generate a means just try to see today, go to the kitchen and take the lighter, and when you will means punch it, when you will press it, there is a spark is generated. Try to see that spark, the direction of that spark, and again press it. Now see, again try to see the spark direction. This direction, like if this is the circular periphery at the bottom part, when you will spark it first time, there is a possibility that this spark can be moved in this direction. When you will next time you will press it, this spark can be in other direction. So there is not a uniformity. This is generated at in any direction at the 360-degree or at the periphery of this piston, or like not piston we can say, but the whatever the cross section that is given to you, it is generating in any direction. Okay, but if we talk about the in the oil, then it will be like what, wherever the minimum gap is there, there only this spark is generated. So guys, are you getting my point? Here the concept of the spark we are taking into consideration, and is it's mentioned that this spark is more predictable and uniform in the oil, so that we are using the oil as well. Now there is a possibility, guys, that this whenever this we are sparking inside the oil, so that oil can be burned. Okay, there is a possibility. So if this oil is basically the ionized, then definitely there is a burning, because if you will spark in front of the petrol, in near to the petrol, then definitely it will burn. So we are keeping in mind that whatever the oil or the fuel that we are oil basically we are using, that is deionized. Please keep in mind this one, guys. So now they came up basically with the idea that this spark is more uniform and the predictable in the oil than it is in air. So they generated the idea that using the controlled sparking as a method of removing of the material. So the same, like if we can like here we are just I'm just talking about a simple lighters. So there are a lot of igniters or other things which is available nowadays, so that they are increasing this spark. And if they are increasing this spark, then this spark only we are using to removal of the material. Okay guys, so this is basically the principle or the literature or the working which we are going to discuss. So they developed basically a Lazarenko circuit, because here we need to generate the spark, so we have to use the electric energy. So they developed basically the Lazarenko circuit. We are calling it as a Lazarenko circuit, or in other words we are also calling it as a relaxation circuit. This is basically based on the resistance and the capacitance. Resistance, which is a R, here we are representing capital R, and capacitance, which is capital C. Okay guys, so okay, so this is this is the Lazarenko circuit, or we can say that is a relaxation circuit. Now what is the elements are, if you will see guys the book, then they are basically on behalf of this one, these kind of things is mentioned, which is a electrical component only, diode we can say. Okay, so I'm not considering that one, because I do not want that you should completely move toward the electric side and you understand nothing. I want that you should understand something. So that's why I'm using, wherever there's a possibility to use the mechanical equipments, I'm using that one. Okay, so that will be easy to understand for you guys. Okay, so this is basically the DC power supply. Okay, DC power supply, again the same like how we were using in the ECM process. So here this is the DC power source. Now one side of this anode side we are connecting, sorry, cathode side we are connecting the resistor. Okay, so this is the resistor. Okay, resistance, because this circuit was based on the resistance and the capacitance, so both the elements we are using. Now here this is the resistance and this is the capacitor. Okay, the capacitor, the purpose of the capacitor is to store the energy. Okay, and then it will start releasing after some time. Okay, wherever there is a need. So what we are doing is we are using this power supply, and we are charging. Once we will initiate the power, it will basically flow the current, and this current will be flow that time basically. Okay, when this current is flow, that time this is charging the circuit capacitor. Okay, and once this capacitor is charged, after that we are using this circuit. Okay, please keep in mind this one. I will brief you. I'm just here briefing you, but I will discuss detail in the analysis part. Okay guys, so once we are charging, first we are charging this capacitor by using this circuit. Okay, RC circuit, and once this is completed, this is fully charged, 100% charged. After that we are using this charge capacitor for this a machining purpose. Okay, so it's not like directly we are using this DC power. First we are storing that into the capacitor, then we are using this energy. Okay, now here this is when you will use this one. So current will be passes in this direction. So this is the tool. Okay, and this is the workpiece. Now initially this workpiece and the tool was like this. initially it was like this, okay, but as the minimum gap is maintained and the spark is generated between the gap between the spark piece and the tool. So because of that spark, the material is removed. Now how this material is removed, I will brief you in the next that is working part. So this material is removed, okay, whenever as we are moving the spark piece towards the downside, so minimum area should come in contact. It is removing the material, and then we are giving a feed mechanism, so it is moving towards the downside, okay, so that minimum gap is maintained and material should be removed continuously, okay. So after some time this position will come out, okay. Now here please guys, you can mention that where's the dielectric fluid. So here I forgot to mention, but I did not forget to mention, but I did not make that diagram. So here basically we are maintaining everything into the container, okay. So here basically this is the dielectric fluid, or in some of the book, either in some of the books it will mention like this, that we are using the dielectric fluid, and some of the book it will mention like they are basically using a separate tank of the dielectric fluid, and they are basically directly using through the hoses or nozzles, we can say. So because the deposition of this ionized fluid, deionized oil is required only where the spark is generated, okay, then only we can say that it is a uniform. Now I will show you that exact meaning of uniform in next slide in the working part, okay. So if this is a gap that is maintained between the workpiece and the tool, then it here in between these gap there is a dielectric fluid is there, and because of that dielectric fluid, and we are supplying this electrical energy by using this capacitor, by discharging the capacitor also, we can say. So it will generate this spark in the minimum gap, okay, and because of that the material is removed from the workpiece area, because there is a possibility that material should remove from the tool side as well, but is you are aware that the tool strength is greater than the workpiece, okay. So but it doesn't mean that there will be no removal of the material from the tool area. Definitely there will be a wear as well of the tool, okay, but here the more it has a less strength, so material will be removed more from the workpiece side. So this is how, this is the basically the principle or the mechanism, we can say, guys, okay. So let's move to the working part. If this or the principal part, we can say, this is just like principle is most probably I have discussed in the previous slide only. So let's go to the principle. So this is basically the tool, and this is the workpiece. So these are generally if we want to make the workpiece, okay, if we are using the workpiece, then definitely there will be a surface irregularities. Surface irregularities means these kind of surface roughness will also be there, okay. This is, by the way, I have mentioned this is greater, but it is very small, because anyhow we are making it the tool for the for the conventional machining operations, this workpiece, okay. So if it has we are not maintaining the good surface roughness, so it has some surface irregularities. Now when it has a surface irregularities, and this is connected with the power supply, so the power is initiated, DC power supply we are using. So whatever the minimum gap is there, for an example, let's see, by the way, this is same. If you will sketch any line, then whatever the minimum, if you will see this one, this element, then this is that has a high surface roughness, okay, as compared with the others. So first what will happen, that when you will move in this direction, you will feed in this direction. If this is the minimum gap, okay, this is the minimum gap which is required to generate the spark, then there will be a formation of a spark. Sorry, there will be a formation of a spark, and because of that spark the material is removed. Now guys, what is the meaning of uniformity here is, uniformity means wherever the minimum gap will be there, that time there will only be a spark will be generated. So what we, this is the uniformity. Otherwise what will happen, when we'll do it into the air, that time this spark will be generated in any direction. So here the direction is defined. What direction? Minimum gap. Wherever the minimum gap is there, there only the spark is generated. So what we have to do, if the material has been removed, once the spark is generated and the material has been removed, then it will, other elements, other surface irregularities will come in contact with the other part, and that will also generate this spark, and that will remove the material. Similarly happen with the others, okay, this will generate this spark and that will remove the material. These things will happen, and this is only the mechanism to remove the material. Okay guys, and once the spark material is removed, once the material nearest material is removed, what we have to do, we need this material removal rate in uniform way. So we are connecting this tool, this we are keeping this workpiece over a table or anvil we can say, and we are connecting this tool with a feeding mechanism so that a constant velocity is maintained, and because of the constant velocity the constant gap is maintained and there will be a continuous removal of the material. Okay guys, so this is basically the principle now and the working part. So now I'm just briefing that what I have just written there. So in EDM process, a potential difference is applied, okay, between the tool and the workpiece using the DC power source. Both are materials that are conductor of the electricity. Yeah, I forget to mention. Please keep in mind this one. Otherwise, there will be no removal of the material, because if we are talking about the chemical or the fluid oil that we are using, that is a deionized water, and if we use the the material which is not the conductor of the electricity, then there you just apply the electricity, there will be nothing. Okay, so tool and the workpiece material are immersed in a dielectric medium. As I already mentioned that whatever the things that we are doing, we are just keeping it everything inside the dielectric fluid only. But here we cannot say this is a electric circuit, or sorry, not electric circuit but electrochemical circuit, or we cannot say this is a EC cell. Reason is, here there is no ion displacement, no ionization, because we are using the deionized water. Okay, so we cannot say this is a EC cell. So generally kerosene and the deionized water we are using for the dielectric medium. Please keep in mind this one guys, this is the best example and freely available. By the way, kerosene is not freely available, but deionized water we can just generate, we can just make it. Okay, a gap is maintained between the tool and the workpiece and the servo mechanism. For this gap only the material is removed. Okay guys, and the servo mechanism is used to control the constant gap. Okay, so to make a constant gap we are using the fitting mechanism, that is servo motors. Okay, depending upon the potential difference which is applied between the gap and the tool and the workpiece, because of that only the electric field is established. As I mentioned that wherever the minimum gap it will found, it will create a discharge. Now you can see that here only guys, please keep in mind, again I'm repeating, here it is not a arc, it is a spark. Okay, what is the meaning of spark? That is, spark is generated for few microseconds only. Okay, and arc is generated for a long time. Okay, so this is a spark is generated where the minimum gap is found, and another is like is the minimum gap is maintained. Now we are giving it feed towards this side, so next spark will be generated when the next irregularities will come in contact. Okay, now these irregularities will be maintained from both the sides, from the workpiece and the minimum side. Like for an example, if we are using this one, so here we can see that here we can see that this is the minimum gap. Okay, so first spark will be generated over here. Now as you will move toward this side, now we can see next to, we can see that this is a minimum gap, so next spark will be generated over here. So please keep in mind. Okay, so next spark will be generated over here and that will remove the material. Now what kind of shapes can be created by this? Like for an example, I want to make on the surface of the workpiece, I want to create these kind of geometries. Okay, this is a semi sphere and this is a V kind of notch. Okay, so we have to we have to create the same geometry over here. So what we are doing is we are just making a replica of that over the tool side. Now similarly, what we were doing in the ECM process also we were doing the same, that we are making a replica of that on the tool workpiece. So that because of the minimum gap, it is moving, and that surface or the material is removed from the workpiece area as per that cross sectional area which is coming in contact. Okay, so similarly here is also happening, we are moving these tools towards the workpiece side, and there is a dielectric fluid is maintained, and big spark is generated. Why spark will be generated? That initially, just keep in mind, if this is I'm talking, this is the surface. Okay, this is the surfaces, this will be the minimum gap initially. Okay, as you will move toward the these tools toward the workpiece side, so this will be the minimum gap. So material will start removing from this area, from these areas. Okay guys, so now here you have to keep in mind one thing, that whatever like the shape of that we have to create. Okay, here we have to create, you will answer me that way what.
Hello, sir.
Yes,
सॉरी सर सर मेरी बैटरी डाउन हो गई मैं सर घर में नहीं हूँ खाली 3% बची है सर प्लीज अगर ये स्विच ऑफ हो जाएगा तो अटेंडेंस कंसिडर करना
Leave.
3% है बैटरी खाली
Leave. So guys, there's a minimum gap. So this is the minimum gap we have to maintain. Okay, and so this is the minimum gap that is maintained. Okay, so you just tell me the answer either today or tomorrow in the next session, that what we have to do. Means if we have to create, like for an example, this is the same size, if like this size we have to create it, we want to create, and the same replica of that is we have patched up, or same dimension of that we have created over the tool surface. Then how this material, is it like a same amount of the material will remove from the workpiece area, or it will be greater than that, or it will be same? Because why I'm asking this question to you guys, please, because as we are moving this work tools toward the workpiece side, and there is a material is removed due to the sparking as well as the minimum gap. So if you will move toward this tools toward the workpiece side, then this cross section area will also create the minimum gap after some time. Okay, so what dimensions we have to select over the tool surface, okay, when we are taking in making the replica of that. Okay, so you should answer me because after some times,
smaller than the
like
shape we need.
yes, Aman.
We need a smaller shape than the shape we need, because we need to keep a minimum distance on all the surfaces.
Or means so we have to we have to take a we have to
Make the
consider
die
the less,
smaller
make the die
than the actual
smaller.
shape. Than the actual shape.
But if you will make the die smaller, Aman, then like whatever the shape is required, that is not created on the workpiece. Because for an example, just consider that this spherical semi-sphere I want to create, and that is of like 10 mm in 10 mm of radius. And if you are considering that this replica of that is less than 10 mm, just consider it is 8 mm. So, and you have to maintain a minimum gap. So whatever the shape that you will create will it be a 10 mm dimension?
No, sir, it will be at if we keep a 2 mm minimum distance, then it will be the shape of a 12 mm 12 mm depth.
Yeah, 12 mm depth.
Because
Right.
Because we will have to keep the minimum distance from both sides.
Both the sides, exactly.
On right
Right.
and 2 mm on left.
Right. So, but when you will think about of these surfaces, Aman, if you will see, when you will see about these surfaces, then if you are moving this one toward this side, if you are maintaining the minimum dimensions, then after sometimes these surface will also come in contact with these surfaces. So there may be a possibility that these surfaces will also start removing the material.
Yes,
right?
sir. Yes, sir.
So what we have to do?
So I will think on that.
Yeah, you should think. That's why I'm asking that you should think of it, and today or tomorrow, you can answer me, guys. Okay, or in the next lecture, guys. Okay. So this has actually happened, that actually I need the surface of this one, but as I have inserted this inside, but only this much area, means actually this I need this surface which is of this hemisphere diameter radius, but actually I get only this one. Now please look at this one. I'm just merging this one. So now actually I got it like this only. So is it like the required one, or it is lesser than that? It is the lesser than that. It is not the required one. So what we have to do? So for that, you just think of it and tell me in the next lecture. Okay, guys. So this is the principle. So let's move to the working part. By the way, maximum things I have mentioned you guys. So I'm just briefing. It will take 2 minutes. So here, first thing, first assembly I'm using, that is this is the DC power supply. The second assembly which we are using, this is the reservoirs. Okay, I will brief you that why we are using this one. And third one is basically the tool and the workpiece geometry. Okay, so first we are using this DC power supply. So the current is flowing here. Okay, so the current is, again, we have to maintain electric circuit. Okay, so electric circuit will, when we are making, as I mentioned in the previous, that generally if you will read the book, then there this kind of diode is mentioned. Okay, this kind of diode is mentioned. On behalf of that, I'm using, this is a tool and this is the workpiece. Okay, so this is the tool. This is the tool. Okay, and this one is basically the workpiece. So now this tool is connected with this side and workpiece is connected with the this side. Okay, so now let's move to the next one. This is the power supply about that. Okay, and next is the reservoirs we are using. So this is the main reservoir. This is the main reservoir where the dielectric fluid is sorry, deionized, or yeah, dielectric fluid also we can say, that is filled. So now this deionized dielectric fluid is basically we have to insert inside the workpiece and the tool where the minimum gap is maintained. Okay, so either we can use it on the other side as well, but to make a uniformity, we are using that whatever the shape of that we are using, in between that only we will create, here basically we are using a cylindrical tube, so cylindrical tool. So in between that only we have created a small passage, through that this dielectric fluid is coming. So now this dielectric fluid, as it is coming toward coming here, then it is spilling towards both the directions. Okay, because both the side gap is same, so it is flowing both the in the both the directions. Okay, so this is how it is coming out now. Is the electrics, so now whatever the like I'm discussing the second one. So now this whatever the fluid which is coming over, depositing over here, that is basically taking toward this side, and another, there is a another reservoir is there. Okay, so whatever the dielectric fluid that is coming toward this side, that is basically reserved in this reservoir. Now after that we are using the filters. So filter is basically we are using, because whatever is spark is generated, because DC, we are using this DC power supply, so spark is generated and the material is removed. Okay, and the purpose of using this this passage is that only, that whatever the spark is generated and the material will remove, whatever the material is deposited, or the material which is removed, that will be like, that can be flow with the dielectric fluid, because it has some velocity when it will be entered in the mediate, in the intermediate. Okay, so it will have a velocity, so they will basically carried out these material which is removed, or we can say they can create a slurry. So now this slurry is moves towards the reservoir, this reservoir. Okay, and here we are using this filter. So why we are using the filter? Because this material which is removed, we do not want that it should move again. If it will should, if it would move again, then there will be a less wear rate. Okay, means the advantage, it will become a disadvantage or demerit, we can say. So we do not want that it will create a hurdle for the next removal of the material or next spark. So that this abrasive slurry should be we are using this filter. Okay guys, so this is basically the working mechanism. Now what I have written over here, that is controlled pulse generator is used with the DC power unit. I will brief you in the mechanism part about the generator when we will talk about that. Okay, please keep in mind, this is the first point about the working of that. Okay, controlled pulse generator. The gap is maintained between the workpiece and the tool to remove the material. Okay, the power supply voltage is depends on the spark gap, what minimum gap we have to maintain, or if we are increasing the gap, then if still there spark is generated, then we have to increase the power supply. Okay, so that power supply is depend on the spark gap, which needs to be maintained constant. Okay, and therefore the servo mechanism that I already mentioned in the previous one. Okay guys, so we are stopping up, I'm stopping up to here. So guys, if you have any doubt, I'm giving you 1 minute. Okay, so you can ask me by the time I'm taking your attendance.